moving to the second presenter, Molnar Kata from Atom Key Debrecen. So Kata, it's all yours.
Thanks. Just a sec.
Yeah.
Can you see it properly?
No. So I see the presenter mode.
Okay. Then I retry.
Okay.
And now?
Yeah, perfect.
Okay. Okay, so can I start, Arthur?
Yeah.
Yeah.
Yes, it's all yours.
Thanks. Hi, everyone, and welcome. Thanks for joining for this afternoon section. And after Sandro's presentation, I will talk about the timescale of volcanic eruptions. And my main focus will be on the geochronological aspect of it, how geochronology can help us defining the different timescales of the volcanic eruptions, the lifetime of volcanoes, and with a special focus on the uranium, thorium, helium geochronology. So in the past few months, several eruptions, of course, occurred, but several eruptions reached the attention also of the public. And at least in Hungary, it felt like more eruptions and more volcanic activities present in the general media. So I'm sure you are familiar with this eruption, or at least with a few of these. So I just put a few examples: the ongoing eruption of La Soufrière at St. Vincent Island in the Caribbean, which also was mentioned by Sandro, or the new volcano building up in Iceland, in a Reykjanes Peninsula, where in the last 800 years there was not much activity. Similar style eruptions going on in the Reunion Island, and a bit different style, a bit more life-threatening is this ongoing La Soufrière, and also at Pacaya in Guatemala. So these eruptions, and I think every eruption which reaches the public, it helps to highlight the really importance of present-day volcano monitoring, and to try to predict better and better the volcanic eruptions to save lives, those who are living around the volcanoes. And this volcano monitoring, of course, done by mainly gas monitoring and geophysical monitoring, geophysical data, satellite images, and also surface elevation monitoring and the changes in the surface elevation. But also, it's very important to know the past eruptive history of the volcanoes, even though if they are not so active at the moment, and to know the style, which type of eruptions occurred, and to know the timing, how the quiescent and active periods followed after each other. So the past events and when the past eruptions occurred, if we don't have any historical written or drawn data on it, the only tool we have is the geochronology. And I think argon-argon and potassium-argon dating is probably the most widespread method to date past volcanic eruptions, especially in cases of young, so let's say younger than 1 million years old eruptions. But it has, of course, as every method, the disadvantage if you don't have xanthine crystals or K-feldspar or unaltered ground mass in your erupted material, then it makes the dating method not suitable. Of course, if the eruptions occurred younger than 50,000 years and you are lucky enough to find charcoal pieces in your pyroclastic deposits, then also you can use the radiocarbon method, which is very precise, having usually low uncertainty in the reported ages. But of course, it's also not always the case that you find nice charcoal pieces in your erupted material, especially if you have a lava dome or a lava rock in certain cases. So the focus in my presentation will be on the zircon mineral. It's a silicate, a zirconium silicate mineral. You can see this pinkish one here in this heavy mineral fraction, and these are also zircon crystals individually or within the rock. So the importance and the advantage of this crystal, of this mineral, is a very widespread accessory phase in most volcanic products, and especially in those type of volcanic products when usually we can expect a long lifetime and periods of quiescent and active eras in the lifetime of volcanoes. So the uranium, thorium, helium geochronology uses zircon also quite widespreadly. So now in the following section, I will just give some basic introduction to the fundamentals of this method and some applications how it can be used. So to the first of all, what's the meaning of the uranium, thorium, helium age? Because it can be used, mainly it's used in a thermochronology sense. So when they are trying to figure out the cooling history of an exhumating mountain or a cooling of an intrusion, uplifting history, which are nothing to do at the moment or for us with volcanoes. However, so the helium method has a quite low closure temperature, so below 200 degrees in case of zircons. So if we are talking about an eruption where the temperature of the erupted lava or pyroclastics or the magma cools down from, let's say, 900 degrees to surface temperature, if it doesn't get further reheating, then the helium age can define also the eruption age of the volcano, which is, I think, very useful tool. So I think probably you are familiar with these decay chains, which are mainly presented in terms of uranium lead methods or uranium thorium methods. And we're going to use the same principle. So we have three radioactive isotopes, the uranium-238, the uranium-235, and the thorium-232, which are in a series of decay events, reach the stable lead isotopes, the 206, the 207, and the 208. In case of the helium dating, the uranium-thorium-helium method, we are using the fact that these decay events or part of these decay events are alpha decay, which are producing helium-4 isotope. 8 isotope is produced by one decay, full decay event, the 238 uranium, 7 from the 235 uranium, and 6 helium-4 isotope is produced by the 232 thorium decay event. So if these produced alpha helium-4 isotopes are accumulated in the crystal, and we can measure, then we can define the uranium, thorium, helium age. The zircon is here comes basically the importance in case of young eruptions, so younger than 1 million years old, let's say. So zircon incorporates quite a lot of uranium and also thorium at the time of the crystallization, around, let's say, in average 1000 ppm, which means that even in case of young eruptions, it accumulates enough helium. And here the enough is meaning, it means that it can be detected with mass spectrometers in our labs. So let's say if you think of an apatite crystal that incorporates much less uranium and also thorium into the crystal structures, so that's not so applicable for very young eruption events, because basically not enough helium is produced to be able to detect in the mass spectrometers. But with the zircon, this one is not a problem. The only concern with this method, that since we have a decay series, we have a decay chain and not just one single decay event, we have to take into consideration the effect of the secular equilibrium, which is the main principle of every geochronological method. So if fractionation occurs at the time of the crystallization and one of the daughter isotopes also gets incorporated to the crystal structure, then the secular equilibrium is not valid anymore, but we have a secular disequilibrium state. In case of zircon, the only daughter isotopes within the 238 uranium decay chain we have to take into consideration is the 230 thorium isotope, which has a half-life of 75,000 year. This often incorporates into the crystal structure of the zircon at the time of the crystallization. So it means that we reach the secular equilibrium only 350,000 years after the time of crystallization. So it would mean that volcanic eruptions or zircon crystals younger than these, we are not able to date with the uranium, thorium, helium method. Luckily, there is a solution for this. So even since this seems a bit too far from the present, this 250,000 years, and plenty of eruptions, of course, happened younger than this, which would be also nice to get information about. So luckily, if we can define the eruption, the crystallization age of the same zircon crystal, what we are using for the uranium, thorium, helium method, then we can, with the two age, with the helium age and with the crystallization age, we can define the true eruption age of the system. So the helium age will mean, let's say we have a helium age of 35,000 years, but we consider that surely secular equilibrium is present, which of course won't be the case because we are far younger than 350,000 years. But if we define the crystallization age of the same crystal with the uranium thorium method or the uranium lead method, then, which is, let's say, 80,000 years, then we can correct this age and we get the true eruption age, let's say 50,000 years. So what do we have to do? What do we have to do if we have a sample with an unknown age and we would like to know, we have a volcanic sample of an unknown age and we would like to know its eruption age. So first we have to find a suitable grain, suitable crystal for the measurements, meaning its width is a minimum 60 or 70 micrometer. It doesn't have fissures, it doesn't have inclusions. This we are defining in a binocular and a polarization microscope before we are selecting the crystals. So we select one full crystal. And then, since we are talking about young eruptions, we want to know first the crystallization age of the crystal. That can be done if the system is younger than 350,000 years. It's done usually with the uranium-thorium method. If we have older grains than that, which can be also the case in sometimes, then the uranium-lead method can be used. And we have two options: define the surface, the youngest crystallization age of the crystal, or define an interior age, which actually both has its own advantages. Since with the youngest crystallization ages, here these two examples are these surface ages. In this case, we will know the youngest crystallization events within our magma chamber. However, also if we have interior ages, then we will get a better knowledge about the whole crystallization history of that volcanic system. So better to have both, and of course both has its advantages. After we defined the crystallization age of the zircon crystal, we have to define the helium content of the crystal, which is done by usually laser heating and on a noble gas mass spectrometer. And here you can see an example from Germany, from the geochronology laboratory in Göttingen. And after you measure the helium content of the crystal, which can be counted as the daughter isotope in this case, then we dissolve the same crystal what was measured before for the helium content. So during the helium content measurement, it's important not to melt the crystal, just to degas, to lose all of the helium content. And after that, we dissolve the crystal. And in case of zircon, you need quite a strong acidic solution to do the dissolution, since they are quite resistant mineral. It's quite resistant mineral phase. And then after that, with basically an ICP-MS, you can define the both uranium-238 and thorium-232 content, and you can calculate the age of your crystal. Usually from one sample, so usually from one rock, you try to achieve at least 6 to 8 crystal uranium, thorium, helium data on 6 to 8 crystals, which might not seem as a large number. And of course, more can be done, but as a rule of thumb, as a minimum, if you see all the steps and the necessary amount that you need one whole crystal for one whole grain for one data, then it can be understandable why is the low number. And of course, with the geochronology, the accuracy and the precision is always a question. So the analytical accuracy and uncertainty are not extremely high or quite low actually, both for the helium determination and both for the uranium and the thorium determination. However, there is a sometimes large amount of mineralogical uncertainty is present, which is more significant than the analytical uncertainty. So usually the helium ages, the uncertainty of the helium ages are below or around 10%, which can be seen as maybe it's too high, uncertainty, but also if we have only this method to define an age, no other method is applicable, then still better than nothing. And surely this is kind of a maximum, but in several cases it's much less than 10%. So this was basically the methodological part of the presentation. I hope you got a good overview of it, and if you have any question related to this, you can ask at the end of the presentation. Now I would like to highlight few applications for this method and also for other regarding the timescales of eruptions. So this is garnet is, I didn't mention before, it's not the most widespreadly used phase for the uranium, thorium, helium method. However, I wanted to put this example here because I think it's quite cool and shows the capability of the method, since the 79 Vesuvius, 80 Vesuvius eruption. Of course, we know the precise age of it since there are written data on it. But I think it's still striking that even with the helium method, they got quite precisely. Of course, with a bit higher uncertainty than what one would expect or would like to see, but still they got more or less the same result as the known age of the system. And as far as I know, this is the youngest event which was dated with this method. So going back to Zircon, there is a Neolithical excavation site in Turkey, Kata, where they found the map, which you can see here. I hope you can see my mouse. So they interpreted this drawing on the site as someone who viewed a volcanic eruption at that time, and they did a drawing of it. So they tried to identify when this volcanic eruption could happen precisely and which volcano could be the source of this drawing. There were several volcanoes around the excavation site, and this Hashandagi site was the closest or the most prominent one. So few samples were taken where they defined the eruption ages with both using the crystallization ages of the crystals. You can see that they used both rim ages but also the interior ages for two sides. And while for one side they got quite an old eruption age of 28.9 thousand years old, the other eruption age they got from a different phase of this volcano was 9,000 years old, around 9,000 years old, which fitted nicely the age of the archaeological finding. So they could say quite certainly that this drawing depicted the 9,000 years old eruption of this Hashandagi volcano. Another example from the Carpathian Pannonian region is the Csomadó volcano, which is the youngest eruption event in the Carpathian Pannonian region. Here, there was available radiocarbon age showing from a pyroclastic deposit and charcoal sample, and but also uranium, thorium, helium method was applied to find out the eruption history and the eruption ages of this system. And here you can see actually how the process goes with the measurements. So we have the helium data. We have several numbers here, but these are not the actual eruption ages of the volcano, since we are well below the 350,000 years old. So we have to use the crystallization ages to correct. And then you can see it's quite a widespread and long-lived storage system beneath the volcano. So we use the average crystallization age in this case, also partly with the uranium-thorium method and also with the uranium-lead method were used to define the crystallization ages. And by correcting these data with the crystallization ages, we get the actual disequilibrium corrected helium ages, and that defines the actual eruption age of the volcano of that eruption. And it was nicely coinciding with the radiocarbon data, which is always nice to have two different methods with resulting the same age. On the same site, at the Chomadol volcanic dome field, which is the wider region of the Chomadol volcano, we also try to trace back the whole eruption history, the whole eruptive period of this volcanic system using the uranium, thorium, helium method on zircon crystals. And we found out that the eruption event started from 1 million years old and up to 160 scattered volcanism occurred, and with quite long quiescence periods. So you can see sometimes even more than 100,000 years quiescent period, and even between there were not too much volcanic activity. Here we sampled all the possible domes, so we tried to cover every possible eruption. And then from 160,000 years approximately, there was a change in the style, in the eruption style. And we see that the quiescence period shortened and also the style of the eruption changed. So more small domes, more domes were built up. And then at the end of the eruptions, we had large explosive eruptions. Here you also can see the limits of the helium method and the presence of the bit, let's say, higher uncertainty, especially when you try to separate eruptions very close to each other, since let's say at this period between 45 and 55,000 years old, the eruption ages were not, or the uncertainties of the eruption ages were too high to separate eruption events, individual eruption events. But still, we can see that the explosive eruption activity focused in these two time period in the last 60,000 years. Another, and I think that will be my last two examples from the US, where they used not just the uranium, thorium, or uranium, thorium, helium ages, but all the basically available method. So this one is the eruption history of the Mont Saint Helens volcano, while this one is the Lassen Volcanic Center, where, of course, before the famous 1980 volcanic eruption of Mont Saint Helens, here at the Lassen Peak, this was the last activity in 1915 in continental US. So these are also an example of two quite long-lived system where the eruptions trace back until 300,000 years at least. And you can also see a similar, what we see in the previous example, that sometimes quite long, 50,000 or at least few thousand years long dormant episodes occur between the eruptions, which is crucial, I think, information in order to evaluate future possible sites where eruption can happen. So thanks for your attention. And if you have any question, please let me know.
Thanks, Kata. So any questions or comments for Kata? I would have a question, of course. Can you use, for example, tephra samples?
Yes. Yes. So for the uranium, thorium, helium dating, you can use, of course, tephra samples. The only thing is that the tephra sample has to include zircon crystals in it. But if it contains zircon crystals, then you can use it without any problem. So that's quite a big advantage, since the zircon is a quite resistant mineral for weathering. You don't have to worry about that it got weathered or anything like that, because the zircons most likely are not affected by surface weathering,
Mm-hmm.
especially in a short time period.
And with this, an additional question: which is the range that you can use, for example, tephra samples? How old or how young?
Yeah, I think they are using quite old. I mean, in terms of 10 million or even 100 million years old.
Mm-hmm.
For older samples, the additional heating. So if the tephra sample gets buried until up to, I don't know, a few kilometers or more than several kilometers depth, then the helium, because of the heating effect of the burial, the helium can leave the crystal structure. So then you have to know the regional geological story of the area, that tephra layer is not on surface since, I don't know, 100 million years old, but it got buried, and you have to calculate then with that. But you can, by the method itself, you can use also for all samples. And for young, I think the youngest one is this, I don't know, few thousand years old. That's the, let's say, the limit.
Okay.
But I think that will get improved with the improvement of the mass spectrometers and the technique itself. So if the detection limits go down, then younger samples can be also dated.
Okay, thanks.
Thanks.
Any questions for Kata or comments? If not, thanks, Kata. I see
Thanks for
today they're
having me.
quite shy. Thank you for the nice talk.